Hello, and welcome to the Energy 2.0 Society's webinar on low energy nuclear reactions. Today we will hear from Mats Lewin and his presentation titled LENR 101, an introduction to low energy nuclear reactions. This webinar, which is sponsored by the Energy 2.0 Society, is being attended by a widely diverse geographic group that we have seen from the advanced registrations. And so we'd like to thank each one of you for your interest and participation in this webinar. As we hear from Mr. Lewin today, you will be hearing from someone who has written extensively on the subject of LENR. Mats is a senior staff writer at My Technic, Stockholm, Sweden, the major technology weekly in Scandinavia. And he is also the managing editor of Next magazine. Mats received his Master's of Science degree in Engineering Physics from Royal Institute of Technology in Stockholm, Sweden. He has been present at many LENR demonstrations and has written about cold fusion in Andrea Rossi in his book, An Impossible Invention. And in case you're not familiar with that book, it's available on Amazon and also in electronic format. So we're very pleased to have Mats here today to give his presentation. So thank you and welcome, Mats.
Okay, so thank you very much, Bill, for that introduction, and thank you everyone for being here today. I'm really glad to be invited to talk about low energy nuclear reactions, the situations today. And just before starting, I think it's very exciting today because there is so much going on right now, and I think 2016 is going to be a very interesting year from this aspect regarding this phenomenon and the technologies that are coming out of low energy nuclear reactions. What I'm going to talk about today is divided not so clearly, but anyway, into three parts. First, I'm going to give you a historical background on cold fusion and low energy nuclear reactions and some basics to explain what it really is from a physical point of view, even though we don't know exactly what it is yet. And then I'm gonna talk about how I got into this field for real, about Andrea Rossi, the Italian inventor, and his technology, the energy catalyzer, or the ECAT. At the last part, I'm going to talk about what's happening right now and the things that are going on and might come to show up in interesting events in the next future during this year. So let me start. Cold fusion, disrupting energy, and more. And this is the aspect of it that I think is so fascinating, that it's completely clear that if cold fusion, low energy nuclear reactions are for real, they're going to disrupt the energy industry, but so much more. Every other industry will be touched, because energy is the very base of technical progress and progress in general in the world. Energy is needed everywhere. And the thing about energy today, I could say that already now, is that if you look upon energy is something that is controlled by a few powerful entities, organizational countries, through nuclear power or oil, specifically oil. And if you would have such a technology as cold fusion, low energy nuclear reactions, you would be able to distribute the access to energy at a low price in the same way as information that used to be controlled by a few has been distributed today and accessible to anyone at a low price. So it's really a huge change, a huge disruption that would come along with cold fusion as a technology, not only from the energy aspect. But let me start. about talking about what Bill Gates said in his annual letter last year. The most dramatic problems caused by climate change are more than 15 years away, but the long-term threat is so serious that the world needs to move much more aggressively right now to develop energy sources that are cheaper, can deliver on demand, and emit zero carbon dioxide. This is very insightful because what people tend to do when they look at the climate crisis of the pollution from carbon fuels, fossil fuels, is how we could come away from that situation, maybe by reducing our energy consumption, which is important because we need to optimize, but they're only looking at the technologies that we have present today, like solar or wind or even nuclear power then. But not even looking outside the boundaries of what could be possible if you invent something else. And here Bill Gates realizes that that is not enough, because solar and wind is not enough to substitute the consumption of energy that we have through oil, and it's not on demand. You still have the problem with storage, and you need an enormous amount of batteries. And batteries in itself is a technology which includes lots of chemicals, which is a problem itself. So here, what Bill Gates basically says is that we need a kind of a revolution. We need to look forward to find something beyond what we know today. And that's very right. What he doesn't explicitly say is cold fusion could be such a technology, but that is what I believe. And that's the reason why cold fusion or low energy nuclear reactions are so important, that they actually fulfill the need that Bill Gates here specifies: cheap, on demand, and zero carbon dioxide. So what if we could have a technology that would give us clean water to every person on Earth, that would give us a heat source that is clean and doesn't produce smoke or other things that are hazardous, dangerous for your health, like open fires that are used in large parts of the world today to produce heat for cooking and for heating houses. And if you could have cheap energy, very cheap energy, and making it accessible to much more people in the world, and if you could have an energy source that would be so compact that you would have the total amount of fuel for a car's lifetime that would fit into your hand, or if you could have an energy source that will let us phase out fossils, and that would let us phase out nuclear power, and that would let us solve the climate crisis. So what if we could do that? Well, cold fusion does that, should do that, if it is what we believe it is, low energy nuclear reactions. The first time talk about cold fusion was widespread was in 1989, when the two very skilled electrochemists, Martin Fleischmann and Stanley Pons, presented their results from their research at a press conference at the University of Utah in March 23, 1989. So they actually struck the world with a surprise, because they claimed that here we got an energy source that produces energy out of water. And it sounds amazing, but it was actually what they were doing. Yeah, so Fleischmann and Pons had this small experiment with electrolysis of water, which is actually an experiment that's being made at high schools all over the world every day. It's a very simple experiment where you have water in a vessel, and you have got two electrodes, and you put electricity through the water. And in doing that, the water molecules are separated into oxygen and hydrogen. So oxygen is bubbling around one electrode, and hydrogen at the other electrode. What happened in their experiment, this small tabletop experiment, was that after a few days, the temperature in the water was raising without explanation, quite a lot, about 10 or 20 or 30 degrees. And there was no apparent explanation, no combustion or nothing else, no chemical reaction that could explain that temperature difference. And their hypothesis was that the hydrogen molecules bubbling around one of the electrodes that was made of palladium, the metal palladium, they already knew that the hydrogen molecules were absorbed into the lattice of the palladium, because palladium is a metal that actually have that capacity of absorbing hydrogen very well. And their hypothesis was that inside that lattice, with the hydrogen molecules being very close to each other, the nuclei of the hydrogen got so close that the probability of fusing the nuclei hydrogen, the hydrogen nuclei to each other increased, so that actually a fusion reaction is when nuclei are fusing into each other, happened more than would be possible normally. Actually, normally it's quite impossible. You need hundreds of millions of degrees to make it happen. But as in the sun, where it's 10 million degrees, but you have got a very high pressure as well. But their idea was that having those hydrogen molecules inside the lattice so close to each other, the probability for fusion would increase. Now, it wasn't actually ordinary water they had. They had what was called heavy water. Heavy water is a water molecule where you have heavy hydrogen. Now, hydrogen is the most simple element in the universe, with one single proton as the nucleus, with one electron spinning around it. Heavy hydrogen is when you add a neutron to the nucleus. And that just doesn't change the element. It's still element number one with one proton, because the element is decided by the number of protons. But it becomes double as heavy. And so this was, of course, if you can have energy produced from ordinary water or heavy water is a small percentage of the water in the oceans, but it's enough for basically extracting sufficient amount of energy for thousands of years. So that's not an issue. Basically, you would have an energy source that would be clean, carbon-free, and cheap, and infinite. And of course, that created quite a lot of interest all over the world. But also discussions, because the problem was that this, according to known physical laws, was supposed to be impossible. And I'm going to come back to that as well. What happened is that lots of scientific groups were interested, and they started to try to replicate this kind of experiment. And they didn't manage. A few of them saw some faint signs of the kind of reaction that Fleischmann and Pons had discovered, but most of them didn't see anything at all. Thinking about it today, it's not very strange, because Fleischmann and Pons had been working with that kind of experiment for years, and it was a quite complicated experiment to set up. We know that today. But at that time, people didn't pay so much attention as they should to that kind of problem. They basically draw the conclusion that as we cannot replicate this experiment, it's probably a faulty experiment. And what happened was that after just a few months, the kind of discussion turned around in the scientific community. And there was this famous meeting in Baltimore in May 1989 by the American Physical Society, with about 1,800 people present. Not Fleischmann and Pons, they were not there. And what was presented at that meeting was the one after another of failed replication attempts. And in the end, Fleischmann and Pons were accused for pseudoscience, or pathological science, which is basically when you find results that you would like to find, but they're not real. And they were actually ridiculed at that meeting. And people at the end were standing up and applauding. So it was a very strong reaction, which I normally wouldn't connect with scientific work. It was kind of more of a sociological reaction. Later the same year, the US Department of Energy made a report trying to summarize all the replication attempts and studies that had been made during the year into this kind of experiment. And they concluded that the results were not conclusive, and they recommended no funding to be directed towards these kind of experiments and this kind of research. And that basically put the end of a common interest in cold fusion. It became a non-touchable area, and no one wanted to deal with it except very few researchers. And you can find that strange, because I mean, it's such a promising technology from the start. Even though you couldn't explain it directly by some valid theory, you could at least put some money into it and continue doing research and studying it and investigating. But basically, after less than 1 year, the scientific communities decided not to look more at it. So this is what we saw in headlines we saw in some of the newspapers: fusion or illusion. This is Time magazine. How two obscure chemists stirred excitement and outrage in the scientific world. Now, that was the end of it, of the large interest in cold fusion at that time. So now let's look a little bit at how this would be possible. Let me first talk about heat sources in general. So we have basically two kinds of heat sources. The most common ones are chemical. And that's when you eat some food and you have a chemical reaction in your body producing heat, or a fire, or burning oil, burning gasoline in your car, or having gas in a lighter burning. So these are chemical reactions. The chemical reactions are reactions where electrons are involved. Electrons are those small, tiny particles spinning around the atomic nucleus. Then you have nuclear reactions, which are on Earth are much less common, but in the universe they are very common. But on Earth they are very, very rare. So you get basically two kinds of nuclear reactions producing heat. And the most well-known, the most used one is fission. It's when you have large nuclei, like uranium, for example, and you split it into two parts. And because of reasons I'm going to come back to in a moment, you have a release of lots of energy in that reaction, and also radiation and particles like neutrons coming out of the reaction. And fission is the reaction that we use in nuclear power plants, and also in the nuclear bomb, the first nuclear bomb that we had in Japan, in Hiroshima and Nagasaki. The other nuclear reaction that is exothermal, producing heat, is fusion. Fusion is when you have small nuclei, for example, hydrogen or heavy hydrogen, and you fuse those nuclei together to create another element, in this case helium or tritium, which would be hydrogen with two neutrons. And fusion is the nuclear reaction which goes on in the stars and in the sun. It produces heat, lots of heat, actually much more heat per atom than the fission reaction. We have it in the sun and in the stars. Lots of radiations and also free neutrons. To get an idea of why these reactions are producing energy and why there is such a big difference between chemical reactions and nuclear reactions, let me give you this image. Let's imagine that the electrons spinning around the nuclei are like houseflies. A housefly weighs like 20 milligrams. You can see that housefly spinning around the nuclei. Let's say if the electron was a housefly, what would the nucleus be? Well, the proton would be like a metal sphere weighing 36 grams. That would be, I think, roughly 1 ounce, 1.5. And let's take an element like iron, for example, which has 26 protons, if I remember right, and some neutrons, total of 55 nucleons. A nucleus of iron would have the mass of 2 kilos, more or less. It's like 5 pounds. So it's very much heavy. It's much heavier than the electrons spinning around there. You can see that nucleus, and actually the distance between the nucleus and the housefly, the electrons would be like miles, like 5 or 10 or 20 miles. And they're spinning around there, those small houseflies around that heavy nucleus. And you also understand, since all the protons are positively charged, they repel each other. So there must be very strong forces pulling that nucleus together. And when you have reactions in that nucleus, you can also understand that those reactions are much more violent. They produce much more energy than reactions involving the electrons, which are the houseflies that are flying around at miles of distance, just jumping from one nucleus to another one. This is the reason why, if you have the same amount of energy in a chemical reaction, you would need 1 million times more fuel to have the same amount of energy out of the reaction. So that's why the heat produced from one or several tons of burning oil is the same heat that you get from 1 gram of nuclear fuel. This makes nuclear reactions very attractive because you need very, very, very little fuel. And then you also, of course, you don't produce any carbon dioxide. So in the end, nuclear reactions are very interesting for solving the climate crisis. And they have kind of an infinite amount of fuel as well. The backside, of course, that we all know of nuclear reactions is that you have strong radiation and you have radioactive fuel with the fission. And the fusion reaction, you don't have radioactive fuel, but you have radioactive waste and very strong radiation producing radioactive garbage, because every material around the reactors is becoming radioactive. So cold fusion would have all the advantages of nuclear reactions, but not the difficulties. First of all, you got a temperature that is only 100 to 1,500 degrees. So let's go back to the fusion reaction that I talked about before, fusing small nuclei together. The only way that we know how to do that, since the nuclei are positively charged and they repel each other, what is called the Coulomb barrier, it's the difficulty to get those nuclei together and get them very close, because they electrostatically they repel each other. The only way we know how to do that today is to raise the temperature, because when you raise the temperature, you raise the speed with which nuclei are moving, free nuclei. And you need to raise them in the sun, you need to raise the temperature to 10 million degrees. There you got a very large pressure helping also. On the Earth, in reactors, fusion reactors that we are experimenting with, because we don't have them working yet commercially, you need to raise the temperature to 100 or 150 million degrees, because you don't have the same pressure. And that makes the technology very difficult to handle, very expensive to handle. In cold fusion, like with the hypothesis that Fleischmann and Pons had with that lattice, the palladium lattice where the nuclei were coming very close to each other, you wouldn't need that high temperature. You would only need a temperature right 100 degrees up to 1,500 degrees, which makes it much easier to handle. But that is considered to be one strange thing with cold fusion. Let me come back to that. The other strange thing is that you don't have any radiation. All nuclear reactions that we know about have radiation as a sign. Neutrons or electromagnetic radiation, which is called gamma or X-ray radiation. So these two aspects of cold fusion is basically what makes most scientists believe that it's possible. Because all nuclear reactions that we know have radiation, and all fusion reactions that we know need a very high temperature to occur. Otherwise, it's impossible. So these are basically the two main mysteries with cold fusion. There's a third mystery involving the time scale as well. But these are the two main mysteries. Furthermore, cold fusion would have the excellent advantage of high energy density. So only 1 gram of fuel would correspond to the heat produced by tons of chemical fuel like hydrocarbons or petrol. The fuel is not radioactive. It's common and harmless elements like nickel, palladium, lithium, and hydrogen that we have abundantly on Earth. Then you wouldn't have any radioactive waste, and you would also have a very portable technology, small, easy to handle, versatile, in different form factors that maybe could fit into a car, a vehicle, or even to a computer or a watch or a mobile phone. And theoretically, once we learn to know how to handle this technology and develop it further. So all the advantages of nuclear reactions and not the difficulties, not the problem, I think. As Bill Gates said, cheap, on demand, and carbon dioxide free. Too good to be true. Too good to be true. And then that's also one thing that people react on. When it's too good to be true, they don't believe in it. They think it's, well, we can't believe in that. It's too good to be true. But it's not a miracle. There are some mysterious things about how it can happen. But we can observe that something happens. And the thing with cold fusion experiments is the main side of it is that you have a heat which is produced, which is much larger than what is possible to explain with a chemical reaction. You know, I already told you that from the same amount of fuel with a nuclear reaction, you have 1 million times more heat than from a chemical reactions. So you immediately can see that the heat produced from such an experiment, like for example, Fleischmann and Pons, it's much larger than the heat that could be produced from chemical elements being present in that experimental setup. So that's why they had the hypothesis that this must be a nuclear reaction, an unknown nuclear reaction, not the well-known ones, fission and fusion. It must be something else, and they call it cold fusion. So you see the sign of it, but you have the problem that you don't have a theory that could finally explain exactly how it occurs. But it's not a miracle. It shouldn't be a miracle. Let's look back. The thing with the energy produced is that, first of all, it's not, energy produced from nowhere. The basic theory about energy coming out from a reaction is the formula by Einstein. This one, the energy equals mass times the speed of light squared. And what do we learn from this formula? We learned that since the speed of light is very large, a very tiny amount of mass would produce lots of energy. And how would this happen? Well, basically, this formula also tells us that there is no real difference between mass and energy. It's just two different aspects of the same thing. So today, scientists basically say that energy and mass, it's equal. One can be transformed into the other, or it can appear as the other. Energy can appear as mass, and mass can appear as energy. And that's the reason why. If you could transform all the mass in an object by making it go against antimateria, you would have all that mass transformed into energy, and it would be a huge amount of energy from nothing. Actually, when you make a calculation on it, you will find out that 1 gram of mass turned into energy would produce an amount of energy which would be 25 gigawatt hours, which is a huge amount of energy. It's more or less the amount of energy that's produced from a nuclear power plant in one day. It's equal to 570,000 US gallons of gasoline being burned. It's an enormous amount of energy. But in no reaction, all the mass is transformed into energy. This formula is valid for all reactions, for chemical reactions and for nuclear reactions. And although you can't actually measure it, because the amount of mass which is transformed into energy in a chemical reaction is so tiny that it's almost impossible to detect. But there is a slight. If you take the gasoline and you burn it, and you take all the smoke and the rest, everything that comes out of it, and you weigh that, you could theoretically detect a tiny amount of mass missing, and that mass is being transformed into heat. And the difference with nuclear reactions is that the amount of mass going away, being transformed into energy, is 1 million times more. So that's why we need less fuel in a nuclear reaction. Still, we can't actually explain how that happened. Let me show you the most technical slide I have today. And this is an explanation why we have heat coming out from both fission and fusion. So the thing I have here, I think it's in my pointer. Here are the dimension of the elements. So the number of nucleons number of nucleons in the nucleus. We have hydrogen up here, like number 1, and we go all the way to the very heavy elements like uranium here. And the thing about nucleons, atoms, is that nucleons happen to be, let me say, most relaxed around the size of iron here with 56 nucleons. And it's kind of, you need more energy to pull the nucleon together. You need more, it's more tense, the situation in a nucleon in hydrogen over here. than you have in iron. And the same thing for a very large nucleus. So you need more what they call binding energy to pull it together. So when you split a uranium nucleus into two nuclei, you're going to have nuclei which are more relaxed, and some of this binding energy will be transformed into heat. You can also have, you can look at it like this. It's like the nucleus is falling down this slope from here. Now we'll talk about fission. Falling down the slope, and the speed that you gain falling down the slope is the heat that you gain from a nuclear reaction, from the fission reaction. Now you can do the same thing with fusion, and then you see that the slope is much steeper. So when you have a hydrogen nucleus being fused into helium, you see that you can release lots of that binding energy because the helium nucleus is much more relaxed. And that binding energy is released into electromagnetic energy like radiation, gamma radiation, and also into the kinetic energy of neutrons being released. So you can go all the way down here to a iron nucleus. And if you want to split that nucleus, or if you want to fuse it into heavier nuclei, then you had to add energy again. It's like here it's relaxed down at the bottom of this valley, and you have to add energy to make it go upstairs again. Mostly, if you see this diagram here, it's going to be turned upside down, so you won't recognize it. That's a normal way of presenting it. But I find that this is more intuitive, to have the feeling that the nuclei are actually falling down this slope here and releasing binding energy into heat, into electromagnetic waves like gamma radiation or heat radiation, and the kinetic energy of neutrons. So I hope you could understand this picture, because this slide is the most technical one I'm going to show today. Anyway, again, talking about miracles. The problem is that we can't actually explain, we don't have any valid, widely accepted theory how this nuclear reaction, whatever it is, in cold fusion happens. So no one can explain that. But it shouldn't be a miracle. I mean, if you look at Galileo Galilei in the 16th century, so he observed, actually he made the observations through his telescope that the Jupiter had moons going around the planet. And what he understood then, that since I can observe those moons, I understand that the idea that the Earth is the center of the universe and the planets and the stars are fixed on glass spheres around the Earth is impossible, because those moons around Jupiter would break the glass sphere where the Jupiter is attached. Again, when he understood that with his observation, there was already a theory by Copernicus that said that the Earth cannot be the center of the universe. The sun must be the center of the universe. Well, later they discovered that not even the sun is the center of the universe. It doesn't matter. But the message is that the scientific method is based on observations, on experiments. And you should trust the experiments once you can repeat them and see they happen all over again. Even though you don't have a theory, you should trust your observations, because that's the only way you can learn about the world. And if you have observations that go against the theories that you have to find new theories. So even though you don't have a theory for cold fusion, that shouldn't be considered as a miracle. You should look for a way to find a theory that can explain what the observations that you have. Well, you could have another parallel, which would be the Wright brothers flying with their aircraft publicly in 1908. At that time, it was considered impossible to fly with heavier than air flight, with a moderate flight. And they demonstrated that that theory was wrong. Evidently, they could fly. Although, even in that case, you had theories about aerodynamics that had started being developed already in the 16th century or in the 17th century. What happened when they demonstrated that it was possible to fly was that the details of some theories were discarded and others had to be found and developed. Because once you knew that actually it was possible to fly, you had to find new theories. Yet, the situation in cold fusion right now, as the end of this presentation of the history of cold fusion and the basic ideas behind the phenomenon, is that we have more than 100 and published in peer-reviewed journals examples of the replication of the experiment by Fleischmann and Pons and other similar experiments showing that the phenomenon is real. There is actually no doubt about it today, although it's very often very difficult to repeat. What people have also understood is that some very specific criteria must be fulfilled to be able to, for example, replicate the Fleischmann and Pons experiment, like 10 or 15 criteria. I don't remember how many they are. And it has also been demonstrated that those criteria were not present when some famous replication attempts were made in 1989. So today we know why those replication attempts failed. One of the most famous, two of the most famous were made by the California Institute of Technology, Caltech, and the MIT Plasma Fusion Center, PFC. And those failed replication attempts were taken as an argument for showing that cold fusion was impossible. Today we know that they couldn't have succeeded because certain criteria were not present, were not fulfilled. Michael McCuber, a famous cold fusion researcher, demonstrated that in 2004, and then another researcher, Dennis Cravens, in 2008. So we have those published and really well defined in peer-reviewed examples, over 100 of them, of observations of the phenomenon. But we can't explain how it happens. There are hundreds of theories, and most of them are contradictory. And the interesting part of those theories is that actually many of them touches areas which could open up new aspects of our knowledge on matter and energy, and showing that cold fusion, beyond being an energy source that could disrupt the world, might open new aspects of our scientific knowledge on matter and energy, which makes it even more exciting.